The Missouri S&T Mars rover design team has been hard at work over the past year, designing, fabricating, and testing in preparation for the University Rover Challenge. We've approached the 2018 URC task by task, creating specialized systems based on competition requirements. Thousands of hours have been contributed by our team's 60-plus members in order to bring this year's rover, Atlas, to life. Our executive board oversees team operations through the financial, administrative, and technical branches in order to create the framework of a successful team.
The technical branch is broken up into 5 major systems: RoveCore Mechanical, RoveCore Electrical, Power, Science, and Manipulators. The team is now entering the system verification phase, including in-field acceptance testing and task simulations.
The mechanical core of the rover features a suspension geometry optimized for large obstacles, a detachable electronics frame for improved serviceability, and an interchangeable auxiliary mounting system. Atlas deploys the second generation of our one-of-a-kind Mantis suspension. This unique multi-link configuration makes use of a differential bar and custom nitrogen gas springs to provide exceptional articulation over uneven terrain in the extreme retrieval task without sacrificing stability at high speeds. Our carbon Kevlar composite wheels have been coated in industrial polyurethane to improve wear resistance and traction in sandy and rocky terrain. Teleoperation is facilitated by a 3-axis stabilized main camera gimbal with 30 times optical zoom. All of these new features were developed and tested using 3D simulations and fabricated using advanced manufacturing techniques.
The custom power board system conditions and distributes power from an 80-cell 8S10P rechargeable lithium-ion pack capable of 33 volts with a 200 amp maximum continuous discharge capacity. Our custom impact battery management system provides cell monitoring, overcurrent protection, and emergency stop at all times. 6 independent variable frequency drive motor controllers modulate and deliver 3-phase power to 6 permanent magnet synchronous motors. A DSP core applies field-oriented control, providing full dynamic torque response on extreme terrain, even at 0 speed. Each individual embedded device operates as an entirely independent modular IoT endpoint over RoveCom, our custom publish subscribe local area network, providing independent command and telemetry including 1080p, H.265, and coded video. A dual linear base station Yagi maintains a wireless backhaul link in the 900 MHz band, allowing for large object RF penetration. 2 circular polarized omnidirectional antenna onboard rover alleviate multipath interference and provide robust connection over the full range of the competition field.
This year's robotic arm has 6 degrees of freedom with a fully continuous spherical wrist, enabling any desired orientation and position of the end effector within the arm's working envelope. Low backlash gear motors and a rigid mechanical structure enable small, precise movements of the end effector necessary for this year's fine manipulation requirements. A dual manipulator configuration utilizes 2 specialized grippers optimized for specific objects outlined in the equipment servicing and extreme retrieval tasks. The payload of this year's arm has been increased to 10 kilograms to ensure smooth operation at the competition's maximum specified load. Our tilting gimbal camera, along with cameras on each of the grippers, provide multiple viewing angles during operation. Our manipulator's control system implements custom feed-forward cascaded PID joint angle control alongside inverse kinematics to enable efficient use of competition task time.
This year's science plan is based off of our site selection criteria, which utilizes geological and biological markers for microorganism activity, such as cryptobionic soil crusts, washes, and mud cracks. Once a site has been selected, our 3-inch diameter core drill will collect and deposit core samples within a sample cache. The samples will be analyzed on board by our custom FT Raman spectrometer. The spectra collected will be compared to known biological markers utilizing a spectral processor and database. The rover will also collect soil temperature and soil moisture readings, as well as data from a 7-sensor weather array. Back at base station, these samples will be analyzed further through 3 biological assays: a Barrett test, Pseudo-4 test, and nitrate test. These tests were chosen to provide insight into the potential existence of microorganisms at the sample site.
For this year's autonomous traversal task, we have implemented improved computer vision technologies to assist in navigation. Our onboard GPS and magnetometer are used to track the rover's location for point-to-point navigation. We have added a LiDAR system capable of producing a dense 3D point cloud for easy object detection and obstacle avoidance within a 35-meter range. With simultaneous localization and mapping technology, we can create a dynamic map to plot a clear course through difficult terrain, eliminating the need for teleoperation.
None of this would be possible without the hard work and dedication of our team members, as well as the support of our alumni and sponsors. With today's creation, we hope to build the scientists and engineers of tomorrow, while keeping humanity forever curious.